All right, this last video for 5.1 is practice problem, so let's get right to it. Calculate the angular displacement and angular velocity of the minute hand of a clock over a period of 15 minutes. So I drew a little clock here, and our minute hand is going to go in 15 minutes. It's going to go from pointing to the 12 to pointing to the 3. And so that is the angular displacement. You can put that in degrees, but also I would encourage you, because it's a clock, to just use like fractions. So your angular displacement, 15 minutes is a quarter of an hour. So it's going to be 1/4 of 2 pi. That's equal to pi over 2, and never stop there unless the physics problem is an AP problem where you're deriving something. Then you can leave pi in there. But we want to know that it's 1.57 radians. All right, so that's the angular displacement of the minute hand in 15 minutes. The angular velocity is going to be the angular displacement divided by time. This is going to be 1.57 radians divided by 15 minutes. Now 15 minutes, I need to convert that to seconds. So I'm going to multiply by 60 seconds over a minute, and that's going to be 900 seconds. So 900 seconds is the time. And we get a really small number, 1.7 times 10 to the negative 3 radians per second. So things on a clock move slowly unless they're the second hand. And so we have a really small constant angular speed, basically, of that clock. Okay. Number 2. It takes a turntable that plays records 6 seconds to get a record from rest up to its playing speed of 78 RPMs. I know some of you probably have turntables or record players at your house, but if you've never seen one before, it's just a platform that's circular, and it spins a big disc made of wax with grooves in it. Anyway, 6 seconds is the time it takes to get a record from rest up to its playing speed of 78 RPM. Calculate the angular acceleration of the record. So I put the time in as 6 seconds. The record starts at rest, so the initial angular velocity is 0 radians per second. And then 78 RPM is the final angular speed. Now that stands for 78 revolutions per minute. When we work with rotation, we always need everything to be in radians and seconds. So I'm going to convert revolutions to radians. That means I multiply by 2 pi radians per revolution. I now also need to convert to seconds from minutes, and so I'm going to put 1 minute over 60 seconds. If you need help with dimensional analysis, come see me, but I'm assuming that since you made it through chemistry, that you can pick it up pretty easily. 78 times 2 pi divided by 60 is going to be 8.17 radians per second. So I'm going to add that to my given information. And now I have a pretty easy problem. It's just the same as regular kinematics. I have an object that goes from rest to a final velocity of 8.17 in 6 seconds. And so I'm not going to use one of the constant acceleration equations. I'm going to use the definition of angular acceleration. And the change in angular velocity is going to be 8.17 minus 0 divided by 6. So final velocity minus initial divided by time, and I have an angular acceleration of 1.36 radians per second squared. And it's the same idea, right? So after each second, the angular velocity of the record is 1.36 radians per second faster. It's greater than the previous velocity by 1.36 radians per second. All right, last one has the most going on with it. You park your car and turn off the engine. The engine was going at 1200 RPM, and so 1200 RPM, and takes 1.2 seconds to come to a full stop. So that's 0 radians per second. One of the gears has a radius of 6.5 centimeters. Calculate the linear distance moved by a tooth at the outside of this gear while the engine turns off. There's probably like 3 or 4 different ways to go through this problem, but I have chosen one. First things first, everything has to be in radians, seconds, and meters. And so I'm going to take 6.5 centimeters, convert that to meters. I'm going to take 1,200 revolutions per minute. I'm going to do the same conversion that I did in the previous problem, and that's going to give me 125.7 radians per second. Okay, so that's what I'm going to use for initial velocity. I'm going to just make a note of that. Now, again, I have a couple ways through this problem, but basically what I need to have is if I'm going to get the linear distance moved by a tooth at the outside of a gear, I need to know the radius of the gear, and I also need to know the angular displacement. So I'm going to need to find angular displacement. There's a couple ways to do that using kinematics equations, but the shortest path through this is going to be using the kinematics equation that the College Board doesn't put on the equation sheet. So that angular displacement using variables other than acceleration. So I'm going to do 1/2 times 125.7 plus 0 times 1.2 seconds. And that is going to get me 75.4 radians. Now, if you don't remember that equation, you can always use 2 different equations. You have enough kinematics information to find the acceleration, and then use the acceleration to find the displacement using one of the other 2 equations. But this is quicker in this problem. Now, the last thing, I'm going to need to find the linear distance. Linear distance is equal to the distance from the axis times the angular displacement. So 0.065 meters times 75.4 radians. And so that linear distance is 4.9 meters. All right, so with kinematics in rotation, there's a little bit more going on than just kinematics equations, but you've been getting used to that sort of thing in physics problems the entire year. So I think you are ready to give it a go. Good luck.